Okay, today we are going to cover electron spin, Pauli's principle, Aufbau principle, and electron configurations. All right, so if we think about Pauli exclusion principle, we should remember this, but that no two electrons in the same atom can have the same set of four quantum numbers. And the two electrons in the same orbital will have all of the same quantum numbers except for the fourth. So they'll have the same n value, so they'll be the same energy level, and they'll also have the same angular momentum quantum number, which is the second one, which tells us the shape. They'll also have the same magnetic quantum number, which will tell us which p or which d or which f, and then the fourth one is what will be different. Alright, so there's the really short version on that section. Then we have the Aufbau principle and the periodic table. Now, Aufbau principle essentially states that an electron must occupy the lowest energy orbital that can receive it. And beginning in the third energy level, they start to overlap. And so this is where we just have to keep the order straight. This is like a big version of all the different orbitals, but it shows us that we go from 1s to 2s to 2p. You know, we've got our 3s, 3p, 4s, 3d, 4p, 5s, etc., etc., etc. Most of us remember this order from the periodic table, but this is just a reminder that they do overlap. Now, the Pauli exclusion principle also states that, or does state, which we've already talked about, that no two electrons in the same atom can have the same set of four quantum numbers, and Hund's rule is the whole idea that orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second. So for example, if I have a set of, oh, it's not going to stick around, is it? If I have a set of 2p orbitals, we're going to fill 1, 2, 3 first, and then come back and double up, which I think most of us remember. And that all unpaired electrons must have the same spin. And that's typically why we do the up arrows first, just to give us some continuity. So if there were only 2 electrons in the p, they both would be facing up, which I think most of us remember. Okay, so again, this just demonstrates that. As we fill the 2p, we put 1, and then 2, and then the third, and then we would come back and we would double it up. What we would not do, is put one here without putting a third one over here. Okay, now we remember the order for filling orbitals can really be determined two ways, either the periodic table patterns or a diagonal chart. And I do have a copy of these for you, and if you have not already received it, you'll receive it in class. This is just a reminder from last year. If we use the periodic table, we go 1s, 2s, 2p, 3s, 3p, 4s, 3d, is where we start to overlap. That stays, and then also when we get down here, we really go from 6s to 4f to 5d to 6p. I know last year we didn't mess too much with these rows. It's not going to be the case this year. We should know the order. And if you remember from last year, we had those foldable periodic tables that we drew on. So if you're stuck on this, you may want to pull those out to help you remember. This is backwards from what we saw last year, and I think the one I have has the 1s up top, but just to show you a different version, remember we follow the arrows where we go 1s, 2s, 2p, 3s, 3p, 4s, etc., etc. Like I said, the one that I have for you is what we saw last year that goes from top to bottom, but it's the same information. Now for writing configurations, remember the steps are first to find the number of electrons in an atom. We're dealing with most of the time neutral atoms. We're going to get to, in Shakashiri and some other problems, talk about electron configurations of ions, but either way you have to figure out the number of electrons. You identify the sublevel that the last electron will be added in. And then you got to draw out the lines, beginning with 1s up until wherever we need to land. And we add arrows individually to the orbitals until all the electrons have been drawn. Now, noble gas notation, remember, is a shorthand. We're going to do some samples here in a minute. It's configuration for the last noble gas is abbreviated because when we get down below argon and krypton and xenon, they're just long and ugly to write them all out. So, for example, if this was sodium's electron configuration, the last noble gas before sodium on the periodic table is neon, so the noble gas notation would be neon 3s1. Magnesium it would be neon 3s2 because it's the second element in the 3s block. Okay? Now let's do some samples. Okay, if we look at silicon, silicon has 14 total electrons. Well, how do I know that? I find that on the periodic table. Silicon's atomic number is 14, and since it doesn't tell me that it's an ion, I'm going to have 14 protons and 14 electrons. This is going to be a neutral atom. The last electron is in sublevel 3p because it's in the 3p block. So if we had our electron configuration version with the arrows, it would be drawn this way. We can summarize it as 1s2, 2s2, 2p6, 3s2, 3p2. This just identifies the core electrons and the valence electrons, which valence is just the outermost electrons. And I think I defined that right underneath here. Yep, valence shell, the electrons in the outermost energy level that are available to be lost, gained, or shared in chemical bonds. Chapter 8, we're going to reintroduce chemical and ionic bonding. And if we were to do the noble gas notation, this would be, for silicon, would be neon, and then the valence electrons, 3s2. I'm going to try to skirt this in, 3p2. Okay? All right, a few more. Oops, sorry, flew right past chlorine. Here's the same thing with chlorine. Total number of electrons is 17. So here we end up with 5 electrons in the 3p block. And if you look at it, you've got 10 core electrons, which again also represent the neon noble gas, and 7 valence electrons. And remember, when we get to covalent, we're going to talk about why they want to get that last electron in that last hole, and that's why chlorine is going to end up being a negative ion. The chlorine ion, just to kind of introduce this, would be exactly the same, except we would put that electron there, and we would change this at the end instead of 3p5 to 3p6. So when you see ion, don't get thrown. It just means that the valence electrons have been added or given away in order to make it more happy and to make it more stable, because chlorine is now happier if that is in there. All right, sodium, excuse me, same thing. It's got 11 electrons. The last electron is in sublevel 3s. It's going to be 3s1. And again, if we think about the noble gas configuration, we would still be neon 3s1. Wow, that's a bad 3, sorry. Again, this just shows you that all the alkali metals all end in s1. So potassium 4s1, 5s1. Now again, if we're dealing with the sodium ion, everything's going to be the same, except it's going to give away that 3s electron. So the configuration for the sodium ion would be 1s2, 2s2, 2p6. We would not have the well, let me stay there, but we would not have this. If I keep crossing it off, it won't go away, right? So anyway, this would be the sodium ion. I just want to introduce that because that is different from what we did last year. Okay, calcium. I know most of us are pretty good at this, but we've got 4s2, 20 total electrons. Here is the long expanded version. The noble gas configuration for calcium would be argon 4s2. And again, if we're talking about the calcium ion would go ahead and give away these 2 valence electrons, and we'd just be left with our core electrons, and then it would be happy. Again, this just shows the pattern for alkaline earth metals. Bromine, I know we're in good shape and we see these. Bromine is a halogen just like chlorine, so it's going to be in the P5. That's where it's going to end. This is where we really start wanting to use noble gas notation. Again, we would be argon 4s2, 3d10, 4p5. Now I want to mention something. You're going to see some sources that will give you the noble gas notation and only give you argon 4s2, 4p5. And their justification for this is that once the third energy level is filled, it's locked in and it's not going anywhere. I would keep with the one that we're used to, where we would write 4s2, 3d10, 4p5, but I just want to warn you, if you see it that way, it's not necessarily wrong. It's just thinking about once that third energy level is filled, and they put it away. And again, if we're talking about the bromide ion, we would get that last electron, and then we would get to 4p6. Okay? Okay, argon, just to show you again, remember argon is a noble gas, so it's going to be locked up here, meaning that it's full, it's happy, and that's a whole part of the reason why argon doesn't want to share or lose electrons. Just a quick side note, when we do noble gas notations for noble gases, we don't just say, oh, it's argon. Okay, we still represent the valence electrons, even though they're locked up, we still represent those as being the outermost shell. So when we write argon's noble gas notation, we typically write it as neon 3s2 3p6. So we still show the electrons that are in the outermost shell. Okay, another thing that's new this year is there are some exceptions that we have to know. The most common exceptions, and one of your homework problems is going to get you to look at everything like down in the F block and the D block, and there's way more exceptions down there. You don't have to have those memorized. It's just to show you that when things get larger, we get more overlap, there's more exceptions. The two exceptions we should be familiar with are chromium and copper. Okay, chromium is, we would expect it to be argon 4s2 3d4. What really happens is we get argon 4s1 3d5. Copper, same thing. The change is in the fact that we would expect it to be 4s2 3d9. Its observed electron configuration is 4s1 3d10. Not totally understood, but when we get to these D blocks, obviously it's got to be something about the fact that they are more stable to have that full 3d10 sublevel than to have the 4s1. So obviously it's the whole fact that they are happier and they have lower energy with that configuration, so that's what they choose, even though it doesn't follow our rules. Okay, I hope that helps. See you in the next video.